Okay, so let us now discuss some of the long tutorial problems for entropy calculation. So, the first question says that a reversible heat engine operates between two reservoirs at 827 degree centigrade and 27 degree centigrade. The engine drives a Carnot refrigerator maintaining minus 13 degree centigrade and rejecting heat to a reservoir kept at 27 degree centigrade. The heat input to the engine is 2000 kilojoule and the net work available is 300 kilojoule. How much heat is transferred to the refrigerator and what is the total heat rejected to the reservoir at 27 degree centigrade? Okay. So, in order to understand the problem first, then we will go step by step, but remember that during the second law of thermodynamics we discussed that a particular heat engine can also drive a refrigerator where heat can be transferred from low temperature to high temperature. So, when the purpose of a heat engine is to derive heat from high temperature reservoir and do the work. Now, this work can be fed into a refrigerator which will then take the heat from low temperature and throw it to the high temperature region. Now, we will draw the diagram and then we will explain this. So, this is the high temperature reservoir T1 from where Q1 heat is taken in and W amount of work is being done and let us say Q2 amount of heat is thrown into the low temperature reservoir T2. And then correspondingly there is a refrigerator which will, now let us call it W1. Now, there is a refrigerator which will now take heat from low temperature and it will require some work W2 to throw heat to the high temperature. So, let us call that, let us call this as T3, let us call that as T4 and we know the values of T1, T2, T3 and T4. So, T1 is 27 degree centigrade, T2 is 27 degree centigrade, T3 is minus 13 degree centigrade and T4 is 27 degree centigrade. We do not know about W1 and W2, but we know the value of Q1 which is 2000 kilojoule and we know the difference between W1 and W2 as 300 kilojoule, that is a net work. Now, we have to find out how much heat is transferred to the refrigerator, that means we have to find out. So, let us call this Q3 and let us call that Q4. So, we have to find out that what is the value of Q3 and so how much heat is transferred to the refrigerator which is Q4 and what is the total heat rejected to the reservoir at 27 degree centigrade. So, that is this is Q4 because this is minus 13 degree centigrade and how much heat is transferred to the refrigerator which is I would say W1 minus that is the W1 that we have to get. Okay. So, basically you have to calculate Q3 and Q4. So, let us do that. Now, how do we start solving the problem? So, first you have to understand that these kind of problems you need to know that in Carnot cycle the ratio of heat input and heat output is equal to the ratios of the temperature of the reservoirs T1 and T2. And remember we talked about the thermodynamic temperature and which is based on the heat input and output from high temperature reservoir and low temperature reservoir. So, Q1 is 2000 kilojoule, Q2 we do not know, T1 is 827 degree which is converted to Kelvin, it will become 1100 and 27 degree will become 300, this we know. So, this will give us Q2. So, Q2 by 2000 is equal to 300 by 1100 which is 3 by 11. So, Q2 is 6000 by 11, that is that much kilojoule is Q2. Now, once we know Q1 and Q2 we can then calculate the W1. So, W1 is Q1 minus Q2 which is 2000 minus 6000 divided by 11 which is 22,000 minus 6,000 is 16,000 divided by 11. So, we know the W1 and we know the difference between W1 and W2 as 300 and of course, that means all the W1 is not being fed into the refrigerator. So, this is the refrigerator and this is the engine, Carnot engine. So, 300 less is being fed. So, we know the W2, which is W1 minus 300, which is 16,000 divided by 11 minus 300, which is 16,000 minus 3,300 divided by 11, which will give us so 3,000, so 13,000, so 12,700. So, 13,000 plus 12,700 by 11. So, that is the W2 that we got. Now, comes the last part. We know that Q3 by Q4 is equal to T3 by T4, which is equal to, so T3 is minus 13 degree. So, minus 30, so T3 is minus 13 degree means 273 minus 13 will be 260, and T4 is at 27 degrees centigrade, which is 300 Kelvin. So, Q3 by Q4 also we know, and we also know that W2, which is Q3 minus Q3 plus W2 is equal to Q4. So, therefore, Q3 is Q4 minus W2. So, let us see how can I do that. So, again, so we have this. So, I need some little bit more space. So, I will be writing it here. Q3 by Q4 is equal to 260 by 300, and W2 we got to be 12700 by 11. Q3 by Q4. So, let us subtract 1 from both sides of this equation 1. We are going to get Q3 minus Q4 by Q4 is equal to 260 minus 300 by 300. Q3 minus Q4 is minus W2 by Q4 is equal to minus 40 by 300 to 15. So, Q4 is 15 by 2 into W2, and we know 15 by 2 is 7.5 and W2 is 12700 by 11. So, let us calculate that. 12700 by 11 into 7.5 giving us 8659.01. So, we got Q4. So, then we can get Q3 also. We have to just add the value of W2 with that. So, Q4 plus W2, which is 8659.09 plus 12700 by 11. So, let us do that. And we get 7504.54 kilojoule. So, this is what we wanted to get from that. So, you see that in this problem the most important part was to understand that the heat input and heat output ratio is equal to the ratio of the temperature. Once you know that, other things is just manipulations, nothing else. Okay. Okay, let us talk about the next problem. So, 3 reversible engines of Carnot type are operating in series, meaning they are operating based on the output of one engine, the input of other engine is happening. So, operating in series between the limiting temperatures of 1100 Kelvin and 300 Kelvin. Determine the intermediate temperatures if the work output from engine is in the proportion of 3:2:1. Now, you see the setup of the engine is that heat is coming from Q1 going to Q2, then from Q2 is going to Q3 and things like that, and the information is given is that the work output is in the ratios of 3:2:1. So, that is important. So, that we are going to use. So, I am going to need little bit extra space for that. So, let us see that the top one, the T1 let us say, that is at 1100 Kelvin, and then the heat Q1 is taken in from that, and some work is done W1, heat Q2 is thrown into the second one, which is again passing to the next one. Let us say W2 work is done, and then heat Q3 is going to the next one, which is again going to go to the next engine in series. W3 work is done, and then finally, it is going to Q4 is going to the final temperature T4, and the T4 temperature is 300 Kelvin, and the top one is 1000 Kelvin. Okay, so, this information is given. Another information is given is that the work outputs are in the ratios of 3:2:1, which means that, so we know that W1 is nothing but Q1 minus Q2, and W2 is nothing but Q2 minus Q3. So, W1 by W2 is 3:2. Similarly, W3 is Q3 minus Q4, and W2 by W3 is given as 2:1, means 2. So, now using this information we can write down a few equations. What one we can write down equation 1, let us say, and equation 2. So, from 1 we get Q1 minus Q2 by Q2 minus Q3 is equal to 3/2. Rearranging that, we will get 3 Q1 minus Q2 is, sorry, it will be 2 3 Q2 minus Q3. So, now I can divide both sides by Q2, and I get Q1 by Q2 minus 1 is 1 minus Q3 by Q2. Okay. So, I can continue with that. So, 2 Q1 by Q2 minus 2 is equal to 3 minus 3 Q3 by Q2, and we know another information we have that these ratios are in the ratios of the temperature. So, we can write that as T1 by 2 T1 by T2 minus 2 is equal to 3 minus 3 T3 by T2. So, let us simplify a little bit more. 2 T1 by T2 is equal to 5 minus 3 T3 by T2. Simplifying further will give us 2 T1 equal to 5 T2, basically multiplying by T2 on both sides, 5 T2 minus 3 T3. Now, the information of T1 is given to me, which is then 5 T2 minus 3 T3 is equal to 2 into 1100 Kelvin. So, 2200 Kelvin, 2200. So, let us write that equation as equation 3. Now, we are going to use equation number 2, W2 by W3 equal to 2. So, W2 by W3 is equal to 2, which is Q2 minus Q3 by Q3 minus Q4 is equal to 2. Therefore, Q2 minus Q3 is equal to 2 Q3 minus Q4. Now, we can divide both sides by Q3. So, Q2 by Q3 minus 1 is equal to 2 1 minus Q4 by Q3, and I can write them as their ratios of temperature. So, T2 by T3 minus 1 is equal to 2 minus 2 into T4 by T3. Simplifying further, T2 by T3 equal to 3 minus 2 into T4 by T3. Multiply both sides by T3 which give me T2 equal to 3 T3 minus 2 T4. I take it on the left hand side. So, T2 minus 3 T3 is equal to minus 2 into 300, because T4 we know. So, minus 600. Let us call that as equation number 4. So, we have two equations now. Equation 3 is 5 T2 minus 3 T3 equal to 2200, and T2 minus 3 T3 is equal to minus 600. So, subtracting we will get 4 T2 is equal to 2800 or T2 as 700 Kelvin. Now, we are going to get the T3. So, you can use any of these above, any of this equation. So, 700 Kelvin minus 3 T3 is minus 600, or 3 T3 is equal to 1300, or T3 is equal to 1300 by 3, which is going to give me 0.33 Kelvin. So, now we got all the 4 temperatures in the series that is working. Again we use the simple principle of Q1 Q2 equal to Q1 by Q2 equal to T1 by T2, and that is true for Carnot engine alone, by the way. It is not true for other engines. Okay. So, that you have to remember. So, next question, a closed system executed a reversible cycle 1, 2, 3, 4, 5, 6, just like it is shown here 1 to 2, 2 to 3, 3 to 4. So, it is like a TS diagram 1 to 2, 2 to 3, 3 to 4, 4 to 5 and 5 to 6 and going back to 1, consisting of 6 processes. During process 1, 2 and 3, 4, the system receives 1000 kilojoule and 800 kilojoule. So, at this stage it receives 1000 kilojoule and at this stage it receives 800 kilojoule heat at a constant temperature of 500. So, this step is 500 and this step is 400 temperature Kelvin. Processes 2, 3 and 4, 5 are adiabatic. So, 2, 3 is adiabatic of course, because there is no entropy change as you can see, and that is temperature is changing. 2, 3 and 4, 5 are adiabatic. Expansions in which the system temperature reduces from 500 to 400 and 400 to 300 respectively. During the process 5 to 6, the system rejects the heat, and that is the place, let us say I call it Q2. System rejects the heat at temperature 300 Kelvin. So, this is 300 Kelvin as is shown in the diagram. Process 6 to 1 again is adiabatic compression process, where the temperature will come. So, from here till here the temperature will come to again back to 500 Kelvin. So, it is adiabatic compression process. Determine the work done by the system during the cycle and thermal efficiency of the cycle. Okay. So, now that we know the problem, we will go back to this page to work out on this particular problem. Okay. So, we have discussed about how to calculate the work done and heat from a TS diagram. So, it is much easier to do from a TS diagram than from a PV diagram. For example, we can graphically itself we can say that the work done in the whole cyclic process is the area that is enclosed by the curve, that we can immediately say. Okay. Now, only thing we have to have is that we have to calculate the area, and how do we do that? That we have to see. Another thing that we can already mention is that the work done in the process is the total heat input minus total heat output. Heat input is already given, because heat can come through these only 2 steps 1 2 and 2 4 and 3 4. So, Q input is nothing but Q 1 2 plus Q 3 4. Q 1 2 is given as 1000 and Q 3 4 is given as 800, which makes it 1800 kilojoule, that is given. all that we need to calculate is the 5 6 thing, that means the area under this particular curve 5 6, that is what we have to calculate. Now, how do we do that? So, in order to do that, we have to also remember that heat or Q is nothing but T into delta S. That means, by knowing the delta S, we will be able to calculate that. So, let us see how we can do that. So, as you can see that we can calculate the heat that is going out in 5-6 process by breaking into two parts. One is the 3-4, another is 1-2. For example, I use another color just to identify that. Let us call this point as 7. So, you see that the entropy change between 5 7. So, let us write first the formula. So, Q out is equal to Q 5 7 plus Q 6 7. Okay. So, Q 5 7 and Q 7 6, not 6 7, it should be 7 6. So, Q 5 7 is temperature at the level of T 5, let us say, I can say T 5 multiplied by S 7 minus S 5 plus the temperature remains same. So, T 5 again into S 6 minus S 7. You see, because the process is happening from 5 to 6. So, therefore, you have to subtract the entropy from the final minus initial. Okay. So, we know the temperature T 5, which is 300. What is S 7 minus S 5? Now, if you look at S 7 minus S 5, it is same as S 3 minus S 4, because they are parallel lines, right. So, we can write that as S 3 minus S 4 plus T 5 is again 300, and we can write that as, now what is 6 7? 6 7 is same as you can see 1 2. So, it will be S 1 minus S 2. So, 300 into S 3 minus S 4. So, S 3 minus S 4, how do we get that? We can get that again by using the formula that it is dq by T. So, S 3 minus S 4, if we have to calculate then we can see the heat input during 3-4 process, which is Q 3-4 divided by temperature at that level, which is 400 plus again 300 into S 1 minus S 2. How do we get? We have to take the input at 1 2 level divided by the temperature. So, again Q 1 2 by 500. Just notice one thing, during the input process it was S 2 minus S 1, but now we are doing S 1 minus S 2. So, it will be the negative of that. Okay. So, now continuing with that, it is 300 by 400 multiplied by Q 34. Now, what is Q 34? Q 34 is negative of Q 43. Actually, it should be 43. So, Q 43 is negative of Q 34. Q 34 is 800. So, it will be minus 800 by 400 plus 300 into Q 1 2 is just opposite of Q 2 1. I should write 2 1, not 1 2, just to denote that the process is happening from 2 to 1 rather than 1 to 2. Again, it will be negative of that 500. Now, we get all our values. So, it is nothing but 3 by 4 into minus 2 plus 300 into, yeah. So, I made a mistake here, I will just change that. So, I have already divided by 400 here. So, I should not divide here. So, I will just write it again, which is 3 by 4 multiplied by minus 800 plus 300 by 500 multiplied by minus 1000. Okay. So, it should be then minus 600 minus, this is also 600. So, it is minus 1200 kilojoule. Let me see, Q 34 is 800, 400 is 2 minus 600, that is 300, 1000 and that is so minus 1200. So, the heat output is minus 1200. So, now what is the work done? So, work done is now Q input plus Q output, and what is the efficiency is 1 plus Q output by Q input. So, it will be 1 plus minus 1200 divided by plus 1800, which is 1 minus 12 by 18, which is 1 by 3. That is the efficiency of this whole particular engine. So, you have got both the things again. So, you see that it is extremely straightforward to calculate the work done for any complicated cycle, as long as you write that in the TS level. And remember that for Carnot engine especially is very simple. If it is an isothermal process, if it is entropy is increasing, then heat will input to the system, and if it is if the entropy is decreasing, then heat is going out of the system. And by working the area under the curve, which is very simple for this kind of system, because it is just a rectangular graph, it is a line under which you will have to calculate the area. So, it is simple enough that one can calculate the whole thing. Okay. So, going to the next problem. Determine entropy change of the universe if 2 copper blocks of 1 kg. So, 2 copper blocks I have 1 kg and 0.5 kg kept at 150 degree centigrade and 0 degree centigrade respectively are joined together. Specific heat of the copper at 150 degree is 0.393 kilojoule per kg Kelvin, and then this one is 0.381 kilojoule per kg Kelvin. So, we are not assuming that the heat capacity is constant or anything at different temperature. So, what will be the change in entropy? Now, you see that it is a simple problem of heat transfer from high temperature to low temperature. So, let us say, so these are at high temperature, right, T1, and this is at low temperature T2, let us say T1 is greater than T2, and dq amount of heat is transferred from first block to the second block. So, what will be the change in entropy for the whole process is that change in entropy of the first system, which is minus dq by or minus q, let us say, by T, and entropy increase will be plus or T1, and entropy increase will be q by T2. So, that is what we were going to calculate. So, it will be q 1 by T2 minus 1 by T1. So, we have to calculate the q, and we know that q is nothing but Cp dt. Of course, here we have to here we cannot take q to be the same for both the processes. So, let us use this particular formula and do the calculation. So, in order to calculate the final temperature, so we can have this particular formula is that, let us say, the final temperature equal to Tf. So, then the first block, how much heat it will lose, let us calculate that. So, first block will lose the specific heat 0.393 into Tf, it will lose, therefore, it will be 150 minus 150 degree centigrade, we should first convert it to Kelvin. So, 150 degree centigrade is equal to 150 plus 273, 423. So, 0.393 into 423 minus Tf is equal to that is the same as the heat gain for the low temperature system, which is kept at 0.381 in the specific heat, of course, and it is 1 kg. Oh, there is a mass associated with that also. So, this system is 1 kg and this is only 0.5 kg. So, m c dt. So, what is the formula of q? Q is mass into specific heat into delta T, change in temperature. So, mass for the first block which is losing is 1 kg, and then specific heat is 393.393, and the temperature change is this much, whereas the other block is only 0.5 kg and specific heat is 0.381, and it will increase from 273 Kelvin to Tf. So, once we equate them, we are going to get the final temperature Tf. So, let us try to calculate that. So, 0.393 into 423 minus 0.393 Tf is equal to 0.381 into 0.5 Tf minus 0.381 into 0.5 into 273. So, or what you are going to get, we are going to use calculator now. 393 into 423 is equal to 166.24 minus 0.393 Tf is equal to 0.381 into 0.5 is 0.19 Tf minus 52, approximately 52.0, or we can get that 166.24 plus 52 is equal to 0.19 Tf plus 0.393 Tf, or 166.24 plus 52 is 218.24 is equal to 0.19 plus 0.393 is 0.583 Tf, or Tf is 218.24 divided by 0.583, which is 374.34, let us say, Kelvin. So, this is what we got. So, once we got our final Tf temperature, now we have to, now we can think into different ways. Either we can think of direct heat transfer as we discussed above at this point, but in this particular case we are assuming that the whole heat is transferred at the same point. However, if we take a reversible process, then the heat is transferring slowly and the temperature also increases slowly. So, in order to account for that, we have to integrate, the system from initial temperature to final temperature. So, let us calculate the change in entropy for the block 1, which is S1. So, S1 we know that it is going from T1 to Tf, and the formula for that is that m c dt is the change, and the entropy is dq by t. So, m c dt is the dq reversible by t. So, that is the formula that we are using, that we have to use in order to calculate that, which is giving us m c ln Tf by T1. We know the m which is 1 kg, and we c we know as 0.393, and we have to calculate ln of Tf, which is 373.34 by T1, which is around 423. Similarly, for S2 we have to calculate from T2 to Tf. As you can see that the S1 will be a negative quantity because the heat is going out of the system, and S2 will be a positive quantity because it is coming in. This is 0.5 into 0.381, if I remember correctly, 0.381 multiplied by ln of, okay, sorry, I will just wrote it fast enough. So, just let me write it once more. So, it is m, let us say this is m1 C1, this is m2 C2 dt by T, giving us m2 C2 ln Tf by T2, and we know the values 0.5, 0.381 multiplied by ln of Tf. Tf is again 374, not 3, 4.34, and initial temperature is 0 degree. So, 273. Now, let us calculate S1 and S2 separately using calculator. So, we have to calculate ln of this quantity. So, we have a function ln here, and we can calculate the ratios also. It is 374.34 by 423, bracket close, multiplied by 0.393, that is giving us 0.048. As you can see, it is a negative quantity. Now, delta S2 will be ln of 374.34 by 273 multiplied by 0.381 into 0.5, giving us 0.06014. Okay. Now, total S is S1 plus S2. So, as you can see, one part is losing entropy, another part is gaining. So, now if I just subtract this one, I will get that 0.048 approximately. We are going to get plus 0.0121 or 0.21, yeah. So, that is that much kilojoule per Kelvin if initial values are in kilojoule. So, you can see that overall change in entropy is positive, and therefore, it is an irreversible process, because which means that it will not go back. So, we have our experience, right. If a hot body and a cold body is brought together, then what happens is a heat transfers, but one cannot get back again hot body and cold body. So, this is an irreversible process that happens, and that happens because overall change of the entropy, total change of the entropy has increased, assuming of course that there is no dissipation is going to the universe outside surrounding or not. We are just thinking that the whole heat from one rod has come to the other rod. That is an assumption that we are taking here. So, with that we are we are finishing the classical second law of thermodynamics. We are going to start with statistical description of the second law of thermodynamics from the next module, and we will come back to the second law of thermodynamics with a twist, classical approach of second law of thermodynamics, a twist using free energies and thermodynamic relations later on.